Hi, this is Shefali here, and I'm again today with another video. And my today's video is on creating a resilient architecture on AWS cloud. So let's try to understand what is resilient architecture first. So here I'm referring one AWS architecture blog, which is on understanding the resilience patterns. So before moving on, what is resilient architecture? What is resilience? So resilience says that the capability to recover any application when stressed by load. Okay, so load can be maybe the more number of requests coming to the service or through the attacks, which can be accidental or maybe deliberately, intentionally, or maybe failure of any component in the workload component. So in any of these situations, when we have a failure, how resilient our architecture is, right? How smoothly our application can work under these conditions with the continuous operations. That is what resilient is. Now, here is a diagram which is showing you a couple of patterns. And here we have pattern P1 to P5. Now, these patterns, they have some core factors like design complexity, cost to implement, operation effort, effort to secure, and then environmental impact. Okay, starting from left to right, if we see the availability factor, then it's lowest at the B1 and then highest at the B5. So these patterns are not mutually exclusive, and we may decide to implement a combination of these patterns based on our application, based on the scenario that we are going to implement. So let's try to understand what are these factors as an overview. Design complexity. It says that when we are trying to increase resilient architecture, of course, it increases the complexity of our application design, right? So like eliminating the single points of failure, okay, and then distributing resources multiply with replication. So we may have to decide that do we really want to keep the system simple, or we have to be more approximate with our disaster recovery plan. Next is cost to implement. So cost often significantly increases when you implement higher resilient architecture, because we are providing redundant resources, maybe across the AZs or across the regions. So that's another factor. Do we really want the cost to be quite high, or we want the medium or low, depending on the scenario? Operational effort. So designing and supporting the higher resilient systems, of course, it requires complex operational processes and advanced technical skills. So when we are deciding to implement the higher resilient architecture, we really need to evaluate our operational competency. Do we have enough skilled resources and the a required level of process maturity when we think about the operational excellence? Efforts to secure security complexity, it is less directly correlated in the with the resilience. But again, when we talk about resilient and then replicating the resources, we have to think of security for each of the component, and it's good to follow the best practices for the security. And the last one is environmental impact. So this is about an increased deployment footprint for resilient systems, because it may increase your consumption of the cloud resources. And do we really need that for the application? Is it good for the environment? And this point is actually focusing on the sustainability pillar of the AWS well architected framework. So that is about the different patterns. Now, let's deep dive into these multi-AZ patterns, starting from P1 to P5. And then we have the architecture diagram. So we are going to refer this architecture diagram. Now, this is architecture diagram for the P1 pattern. So P1 pattern, it actually introduces the multi-AZ architecture, as you can see. Okay, but we have only one instance in one AZ. So where the applications operate in the multi-AZ architecture, and then this allows your application to withstand the AZ level impacts. It's just the AZ level impacts, and it supports the AZ level failures. So think of the applications which are not very critical, like the applications that deploy their internal employee applications. So in that case, these are the low business impact applications, and therefore it requires a low level of resiliency. So this is about the P1 pattern. In this case, if the EC2 instance in 1AZ goes down, in that case, the Amazon EC2 uses the health checks to automatically detect the faults. And then if an AZ fails, then Amazon EC2 prompts the auto scaling group to recreate the EC2 instance in the other AZ. So we have a trade-off here that there would be some downtime because we are not pre-provisioning any resources. So there would be some downtime because as soon as the one AZ goes down, it is going to prompt uh, the creation of new resources in the other AZ. This is also known as the bi-model behavior. Bi-model behavior says that if there is a fail at one AZ, then only it prompts the other AZ to create the resources. Let's come to the pattern P2. So pattern P2 is multi-AZ with the static stability. Now let's check the architecture diagram here. So you can easily find out the difference between the P1 and P2. So in this pattern, actually we have multiple instances in one AZ. Okay. That is again, it covers the AZ level resilient architecture. Now, this pattern uses static stability to prevent the bimodal behavior. Okay, so this system, it remains stable and operate in one mode, irrespective of changes to their operating environment. So the key benefit of this statically stable system is that it reduces complexity of recovery during a disruption. And it's just due to the pre-provision resource capacity. So think of an application where we have the customer facing website, okay, that has a lower tolerance downtime. So in this case also we have a downtime, but lower tolerance, lower downtime. So anytime when the website is down, it could result in the lost revenue. And because of this, the website requires two EC2 instances that are provisioned with the two ACs, right? So using the health checks, as soon as when the one AZ becomes impaired, as you can see here, the other one would be start in the operational condition. So this is about the P2 pattern. And if we say the trade-offs, then it actually mitigates an AC disruption without downtime. So there would be no downtime. So I would like to change my statement, which I told before. No downtime here to the application clients, but must be weighed against the cost concerns, right? Because we are providing multiple instances and there is no single point of failure. So that is the reason that we are investing more here. Now, this implementing P2, it requires your application to support distributed operations across the multiple instances. Let's come to the pattern number 3, P3, and this is about application portfolio distribution. Now here, let's find out the architecture diagram for this. Awesome. Now, this diagram is actually this is a multi-region pattern, and this is to increase functional resilience. It distributes different critical applications in the multiple regions. So critical applications, think of the banking services, like the credit balance checks, right? Where customers, they use multiple digital channels, like to the mobile app or to the web app. So specific to this example, it says that like region with the customer's mobile application may have a disruption that causes mobile app to be unavailable, but then customers, they can still access their banking application through the web app, which is running in the alternate region. So the regional level disruptions are rare, But implementing a pattern like this ensures that users retain access to their business critical applications. So I hope you got this. Trade-offs, if we check the trade-offs here, so it mitigates the possibility of regional service disruption. That is true. And here the application spans across the regions, as we can see here, region A, region B, and that is why it requires significant operational planning and management. There would be again data sources, isolated functional elements may depend on the common downstream systems. Another pattern is P4. Now, P4 is about multi-AZ deployment, and this is multi-region disaster recovery. So DR is disaster recovery here. Now here, okay, I don't think we have a diagram here, but let's find out what this point is saying. This is again for, like, think of a corporation where it operates several business critical services, not only one, but several business critical services, and that have a very low tolerance for disruption. So during these kind of scenarios, the corporations, they decide what kind of disaster recovery plan they need. Okay, so we have, as you can see here, we have the RTO and RPO, where RTO is recovery time objective and RPO is recovery point objective. So it means recovery time objective says that for how long I can accept my application to be unavailable or offline. And RPO says that recovery point objective, which means that for how much time I can accept the data loss of my application. So when we talk about the different patterns, two are given here, pilot light and warm standby. Pilot, under the pilot light, it actually requires RTO, RPO of tens of minutes. Now, in this case, data is actively replicated and application infrastructure is pre-provisioned. So we have another region where the infrastructure is pre-provisioned and the cost optimization is the key driver here. The reason is that the infrastructure is switched off and then only switched off during the restore event. Whereas another pattern is warm standby. Now, warm standby, this pattern improves significantly as compared to the pilot light by keeping application running in the disaster recovery region with the reduced capacity. As an example, might be your application is um, working on 4 instances, and in case of warm standby, we are providing another region, and in that another region, we are just running 1 or 2 instances, but not all 4. So that is known as the warm standby. We are pre-provisioning the instances which are running, but with the low capacity. So this is, of course, this pattern can achieve RTO, RP of minutes if implemented correctly. If we talk about the trade-offs of this P4 pattern, of course, it mitigates disruption to a regional service while reducing the mitigation cost. But again, we have a significant increase in the cost as well. Let's talk about the last pattern for today, and that is multi-region active-active. So we have a diagram here for the multi-region active-active. Now, what this says that think of the core banking applications and then customer relationship management applications which have zero fault tolerance. So we are not talking about here the low or the minimum of fault tolerance, but the zero tolerance for disruption. In that case, we use this pattern. Now, what happening in this pattern is that we have region A and region B, and in both the regions, the workload is running simultaneously. So allowing them to serve traffic from all the regions simultaneously. Okay, there is nothing like the low capacity which is being provided in the other region, right? Allowing them to serve traffic from all the regions, and this pattern not only mitigates against the regional disruptions but also addresses the zero tolerance requirements. So this is really amazing to check here. We have Route 53, and then we have in region A, AZA, AZB, same in the region B, AZA, AZB, and all the components are replicated and running simultaneously. If we talk about the trade-offs, then it mitigates the disruption of regional service, that is true, but invests additional complexity and the cost to deliver RT of near zero. If you see here, this is RT of near zero. That is the advantage we are getting, but again, we're compromising the cost also. This is known as multi-active deployment because at both the sites it is completely active and they are generally complex to design as well. I hope you like this session. Thanks, and looking forward from my side to create such more videos. Thank you. Bye bye.